lesson on focus and directrix of parabolas. Prior to that, we were working with circles as part of our unit on conic sections. Our unit on conic sections, when we took our cone and sliced it every which way, so that if you do the straight cross section, you have a circle, and if we're sectioning the cone at a slant, then we have a parabola formed. And there are going to be a few others. We'll be working with the ellipses and hyperbolas next, right? So we can have an ellipse when we cut our cone through the vertex at a slant or down from the vertex at a slant. So we're just continuing right now. Yesterday we had one activity with the focus directrix paper where let me get this back up here. We set up different C values, different distances from a focus to the vertex, copied that distance from our vertex to the directrix, and went out the same number of rings and up the same number of lines, connected the dots. We said, oh look, you get a parabola. We had established already a definition of a parabola as what? What did you have in your notes that we were able to determine as the definition of a parabola? Yes?
A set of points in a place equidistant from a given point called the focus and a line called a directrix.
Yes, fix that to in a plane.
Oh.
Okay, because in a flat plane we call it a parabola. In 3 dimensions we have a paraboloid. Like if you think of half of an Easter egg, when you take it in half horizontally and the shape you're holding in your hand is a 3-dimensional parabola or a paraboloid. Okay? So, we got that far, and before then we were working with circles. What is the definition of a circle? Oh no. Who knows? Take a stab at it, Brad.
A set of points in a plane such that the
equidistant from the center of...
I'm sorry?
It's equidistant from the center, or one point.
Perfect.
Circle.
Yeah, and that equal distance is called the radius. Sure. So you guys are doing great. Now we have a question to lead off with that might help us figure out any differences in our shapes. So we've got a telescope lens 12 centimeters in diameter and 2 centimeters in concavity. We want to determine the equation which models its curvature to produce clear images. All right, let me see you draw a picture of this problem to begin with. Draw what's going on. Oh, I love yours. Would you put yours up on board? Sure. True artist. So what is the shape of the telescope lens?
A parabola.
What is the shape of what fits inside the telescope to begin with?
A circle.
A circle. And so now the question, we're going to see a cross-section of how does the lens get ground? You're grinding it down to what kind of curvature to produce clear images. All right? Thank you. That's lovely. So we have 12 centimeters in diameter, 2 centimeters deep, and the circular opening all together. And so this is, I'm going to stick this in here as a dotted line, because here's our lens coming down like this. And it looks round. And we've been playing around with some round things, like what?
Circles.
Circles, what else?
Spheres.
Spheres, right, our 3D version. So, right, but the cross-section of the sphere would give us a circular outline. What else?
Ellipses.
Ellipses. We haven't played around with those just yet, so that might skew our question and answer time a little bit. But what else?
Hyperbolas.
Hyperbolas, yes. What else? and parabola. So we have a lot of choices what equations we might pick to model this. So let's start with one that we had a couple days ago with the equation of a circle, just in case, right? If we were going to superimpose a grid on our picture so that we can get some numbers here, here we would have our origin, and what point would we have out here?
6, 2.
Good, right? We've got our 12 equally split, then we're going out 6 on each half, and a total distance depth of lens. So the 2 isn't all the way down, it's the concavity of the lens, right? So it's just the depth. So this is out 6, 2. And then if we were going to follow our circular path around, this would be our radius. And how much would we have? We'd have another radius here. How much would we have this far? I have no idea. But what do we have in terms of our problem?
Would be radius minus 2.
Good job. Right, if we have 2 right here as the depth of our concavity, then we'd have our radius minus 2 up above it. Does that make sense? All right, then do you also see what relationship you could set up to solve for r? What relationship do you see?
A right triangle.
All right, then what could you use? How could having a right triangle cross section help you figure anything out? Go ahead, take a minute, use the Pythagorean theorem, and we'll look and see what you get. Solve for the missing radius. Excellent. Would you put yours on board? Sure. Thank you. Talk to us. Tell us what you're doing.
Okay, so you have this side right here is r minus 2, so you square that, plus 6, because the distance over there is 6, equals r squared, because a squared plus b squared equals c squared. And then you FOIL that out, so it's r squared minus 4r plus 40, because you get 4, and then this is 36, so you add the 4 and 36 is 40, equals r squared. And then these cancel out. So negative 4r plus 40 equals 0, minus 40 on both sides. Negative 4r equals negative 40, divide by negative 4r equals 10.
I love it a lot. You did a great job. Thank you. Then where would that put the center of our circle? At what ordered pair? 0, 10. Good. So if we're going 10 units in every direction, that also means 10 units from our origin straight up. And so the center of our circle would be at 0, 10. All right. Then what would be the equation of our circle? We have the center, we have the radius. All right. So what would be the equation of our circle? Yes.
Would it be x squared plus y minus 10 squared equals 100?
Perfect. Because we've got 0 for the x coordinate, we have x minus 0, squaring that, we've already got the simplified. Gorgeous. To type it in on our calculators, we would need to get y by itself. So do a little bit of algebra, get y by itself. Let's agree on this first before we type it in. You might, instead of foiling it out in case that's what you're doing, you might think of just undoing. You need to get y by itself. If you foil this out, you'll get y squared and y, making y in two different places. You want to keep it in one place. So how could you undo? Sam, what would you do?
Square root it.
Right away? Would a square root work if you had addition in the middle?
Oh, no.
All right, so give me another plan.
Divided by 10 on each one? No. Or subtract? No.
You have an idea, Stefan?
Yeah, you could move the x squared to the other side by subtracting x squared from both sides.
All right.
And then, once you have y minus 10 squared all alone, you can find the square root of both sides.
Right. Keep going.
And then that's just 2 squared, so 10 minus x. No.
All right, we're having a little bit of a trouble. It's come up twice so far about when you can take the square root of squared numbers.
Yeah.
And since squaring is repeated multiplication, those rules only apply for multiplication or their inverse, division problems. If you have addition or subtraction, the rules don't apply. So go to another plan. How else can you, I mean, if it doesn't simplify, it doesn't simplify.
Yeah.
All right. But what should be in front of your radical when you take your square root?
Plus or minus.
Very good. So we have our plus or minus square root that doesn't simplify, 100 minus x squared. Solving for y now, what do we get? Go ahead.
Y equals plus or minus, oh, the 10 is fine for,
That's fine, yeah, typically it's put in front as a connector, so,
alright, 10 plus or minus square root of 100 minus x squared.
all right, let's finish up one more little thing. Considering the shape of our lens, can you determine whether we want the plus or the minus? Which one do we want?
Plus.
So the y direction goes vertically, right? And we're saying y is the upper or the lower version of our circle. Look at our picture. Do we want the upper half or the lower half of our circle? The lower half, so do we want the plus or the minus? The minus. All right. So then, type this in on your y equals on your calculators, and we'll set an appropriate window along the way to fit our diagram.